Hey everyone, so I'm back. There were a couple of more concepts that I was sort of leading into or dovetailing into from the previous video. And just as a quick review, in the previous video I was talking about 5 types of loads or forces that are put on, well, materials in general. So in materials and engineering we will talk about these forces, but they really are concerned to us because they help us to understand and describe what's going on in the body. And these 5 types of forces were compression, tension, bending, torsion, and shear, right? So those should sound familiar if you saw the previous video. But I also used the term stress. In the previous video, I believe I spoke to it very briefly. And I want to get into that a little bit more here. But before I do that, I want to go to another term that I also mentioned in the previous video, and that is pressure. Without belaboring the point, pressure is force divided by units of surface area. So it gives us an idea of how force is distributed across some surface, right? And it's not too hard of a concept to grasp, I think, right? Drew this beautiful illustration up. So if I can point this to you, if this is some surface, let's say this is our skin right here, and I have a block, something just that has a flat surface, and I put 10 pounds, I press with that block on the skin with 10 pounds of force. Well, that force is distributed over whatever surface area this object has, right? Well, if I do the same 10 pounds, but instead of having this sort of flat surface that covers a reasonable amount of surface area on our skin, it all instead converges to this very small point. Well, this is probably going to hurt a lot more, right? Because it has a tendency to do more damage. It can actually penetrate the skin. And again, this should be relatively simple, right? We know this intuitively, and we probably got it in grade school or in high school at some point and had to do some boring problems, on a test somewhere. But again, the units here are force, so we can have, I think I wrote it this way last time where I just did, force divided by area. And if we wanted specific units, we could say something like, newtons per square centimeter, or what have you, right? Well, we're more interested probably in this idea of stress, which interestingly enough is expressed in the same units. Now, pressure is force distributed over a certain surface area, while stress is force distributed through a tissue or through a material. But the area unit, again, we have area, so let's say square centimeters, but now instead of surface area, this is cross-sectional area. So let's see if I can whip something together real quick here. I've got a cylinder of some kind, right? Try not to botch it too badly. Let's say I got this cylinder, right? And I'm putting, again, maybe I'm standing on it, or I have a weight on top of it, right? Something is pushing down on it here. Well, that force doesn't just magically go from here to here. It doesn't, only act on certain parts, right? Without getting too complicated, you can imagine this force is going to be distributed through this material, right? So if I were to look at the cross-section of this material, right? If I just took a cross-section here, then I would have, of course, if I looked at it face on, some area, right? Just write A, and it's all crooked, I know. But I would have some area there and some force going, I guess, into, in this case, like into the board, right? Into that area. But it's not surface area. We're concerned, when we're talking about stress, we're concerned with the forces that are acting through a tissue at any given point throughout that tissue, not just on the surface of it. Hopefully that makes sense. I can try to address this more smoothly or cleanly in a future video if that confuses people. But why do we care about stress? Well, the amount of stress that goes through a tissue is important because every tissue, every material has a certain limit, has a certain tolerance. So, if you pull on something too hard, it eventually breaks, right? Maybe it'll stretch first, it'll deform in some way, but if you keep pulling on it or pushing on it or twisting it or yanking it or doing whatever you can to it with some kind of force, eventually you can reach a point where that tissue, if we're talking about the body or just some material out there in the world, where the material or tissue starts to fail. And we're, of course, very concerned about that. As personal trainers, as exercise professionals, as people who work in the fitness or health industry, we should probably be concerned with making sure that we're not putting too much load on a tissue. And when you start reading research or reports from experts on proper exercises and surgeries and rehabilitation and all this stuff about injuries and the mechanisms of those injuries, you will see terms like stress and strain, and it maybe helps to know what all that means, right? So I'm going to get my eraser so I can make some room here. So again, stress now that we've seen, is force distributed through an object. We can at least roughly think of it that way. And when we're talking about it, expressing it numerically, it is force divided by units of cross-sectional area. Okay? So in fact, I'll write that over here. So this first one, again, this is just force divided by area. If it's surface area, then that's pressure. But if it's force divided by cross-sectional area, I'll put CSA, then that is stress. Okay? Hopefully that makes sense. Now, like I said, every material, every tissue that we're going to be looking at, that we're concerned about, is going to have certain tolerances and deform in certain ways. And we have this idea of stress and strain. So if stress is the actual force that's being loaded through a tissue, well, strain is the amount of deformation it undergoes. And we have something called a stress-strain curve. You'll see these, and they can be various shapes. They don't all have the same shape. It depends on a variety of things that I don't want to overcomplicate this video with, and I'm frankly not enough of an expert on to really speak to. But the basic concept is this. All right, I'm going to set up my axes here. It's going to be a nice little graph. Yay, graphs. So what we have here, right, is strain on the x-axis. So strain, if we're stretching a tissue, we can say, it's some unit of length. So I'll just put, L, right, some units of length. Maybe it's centimeters. So I could also do that, put centimeters here. Okay. Gotta love my horrible handwriting, right? So that's the x-axis, or the horizontal axis. On the vertical axis, we have the amount of force, or more accurately, stress we're putting through the object. So stress. And again, we have, units of force divided by, units of cross-sectional area, right? So you could have newtons per square centimeter, or whatever you like. But here's the basic idea. You have some, and even the beginning here, actually, there's, very, you have like a slack region, something called a toe region. We're not going to worry about that right now, but the basic concept is this. You get maybe something that looks like this at first. And what this line is representing, or the slope of this line is representing, is how difficult it is to deform this tissue, right? So for every horizontal unit of deformation here, so every, say, centimeter or however many centimeters of lengthening, let's say if we're stretching maybe a tendon, you have to put a certain amount of stress, additional stress through that tissue. And many tissues or many materials have a region that's pretty linear, like this. That is, it's pretty constant. I yank on a thing with 10 pounds, it goes to a certain length. I yank on it with another 10 pounds, it predictably lengthens a certain amount. Another 10 pounds, it again predictably lengthens another certain amount. It's pretty consistent. At some point that starts to change. Like I said before, every tissue has its own tolerances. So at some point we get to a point where maybe the slope is going to start leveling off here, right? And what this means is that the tissue is starting to yield. In fact, it's often called a yield point. A yield point. So this point right here almost looks like a weird letter or something. I should fix that, right? Maybe that doesn't help. But the yield point, this is where suddenly this material is not resisting being stretched or being deformed as well as it was before. That is to say, I've deformed it a certain amount, and now as I continue adding stress, I don't have to add a lot more to start stretching it more and more. So eventually, it becomes pretty easy to keep lengthening this thing. You've probably experienced this. You pull on a plastic bag, or you pull on even a rubber band, right? You may notice before it breaks, right before it breaks, it actually, you may even get stiffer and stiffer, and I'll talk about stiffness again in a second. But it'll resist that lengthening for a point, but at some point it starts to fail, like it starts to get weaker, and suddenly it gets easier to start lengthening it. And then shortly after that point, it starts to fail and it rips in half or something. Well, that's what's happening here. You have this yield point where this material is no longer resisting being lengthened as much or being deformed as much. And in fact, that resistance to being deformed is what we call stiffness. So the stiffness could be expressed by the slope of this line at any point. So it has a certain stiffness over here, has a certain stiffness down here, has a stiffness right here. So stiffness. Excuse my horrible handwriting and very poor organization there. But stiffness, again, is just the resistance of a material to being deformed. That is, its resistance to strain. Because again, strain is deformation. That's what I put down here on the horizontal axis. So a stiffer material resists having its length or its dimensions, its volume, something about it changed as much. I keep saying length because one of the best examples of this is often, at least in the body, is a tendon. So tendons get pulled on and they tend to stretch a certain amount. They have a certain resistance to that stretch, a certain stiffness. And we can talk about tendons a lot and how they might contribute to what we're experiencing when we're exercising, what their role might be, or several roles, what their roles might be in exercise. Another time. Okay? So that's the idea of stiffness. So we've got stress, which is this force going through a tissue expressed as force per unit of cross-sectional area. We have strain, which is the deformation of a tissue. I use the example of lengthening here or stretching something because that's pretty easy, I think, to visualize. And we have this idea of stiffness, that is the resistance of a material to being stretched or to being deformed, right? Its resistance to strain would be a nice kind of broad definition to give it that I think will help you out. Then there are a couple other concepts related to this that I want to get into, and then I'll cut the video off there. And that is this, or those are these, to keep my pluralities consistent here. And these are the concepts of elasticity and plasticity. So when you hear the word elastic, you may think of something that's stretchy, right? An elastic waistband. And I happen to have some trusty shorts here. Don't worry, they're clean, I think. They're clean. But the waistband in these shorts, they're kind of stretchy, right? You can easily see I put a little force on this, I yank on it, put some tension here, and it will stretch. That is, it will deform, undergo a certain amount of strain, depending on the stress I put through the waistband. But the stretchiness, or the ability for me to deform this, that's not elasticity. Elasticity is the quality that this material has to snap back. Elasticity is the tendency for a tissue or a material to return to its original dimensions after it has been deformed, to return to whatever previous dimensions it held. A teacher of mine in anatomy and physiology a long time ago used the term, I'm not making this up, snapbackableness. It's a stupid word, but I use it when I teach my students. I think it gets the point across. It's a goofy enough word that you might remember it. That's elasticity, the snapbackableness or snapbackability of a material. So when you deform it, you squish it, or you stretch it. So that's another thing. It's not just stretching things. If I have a rubber ball or something and I try to compress it, I might be able to squeeze it into a smaller volume, and I let go and it wants to snap back to its original dimensions. That would also be an expression of elasticity. So this often, on a stress-strain curve, this region here, where there's this nice predictable, this predictable stiffness here, where for each unit of stress that you put through the material, there's a predictable amount of strain, and where when you deform it, if you take that stress off, the material will go back to its original dimensions. So that is, where the material, in fact, let me use a different color here, where the material, again, returns to its original dimensions, it's not permanently deformed, right? So say everything before this little sloppy blue dotted line, this would be the elastic region, right? So I'm going to put elastic, just pointing to this whole region here. After that, after this yield point, so that is after you start getting a reduction in the stiffness, well, what's happening there is you're starting to cause some permanent damage or some permanent alteration to the material. And so that is where we enter what's called the plastic region. Plastic. So plastic in this context refers to a permanent change in the state of a material, a permanent change in its dimensions in some way. So basically, if we go far into this realm or this region here, past this yield point, this material is likely not going to return to its original dimensions. So if this is a tendon, I can stretch it to a certain amount and it'll snap right back and it'll be fine. But there is some point beyond which, if I stretch it, especially if I hold it there for any length of time, where it will likely not be able to return completely to its original dimension. I have entered the plastic range, so I'm now undergoing some permanent deformation of the material, of that tissue. And so that's important. Whenever you sprain a ligament, when you sprain your ankle or something, a sprain is often, depending on the materials you're reading, defined as a plastic deformation and overstretching of a ligament or group of ligaments. So the passive structures or the passive tissues that are helping to support that joint and keep it stable have been stretched out enough that maybe they don't return exactly to their original dimensions. And so they don't have as much tension in them at a given length as they did before, and they're not as good at stabilizing the joint as a result. I don't want to go down that rabbit hole, but maybe that gives you a little mental image. So elasticity is the quality of a tissue or the capability of a tissue to return to its original dimensions after it's been deformed. Plasticity is the permanent deformability of something. And when we talk about a plastic change in a tissue, that means it is at least semi-permanently remodeled, or it's changed dimensions, or it's changed its state somehow. Okay? So hopefully that gives you an idea. I've run long-winded enough about stress in a tissue and deformation of a tissue. And when we talk about tissue elasticity, this is at least a very brief overview, very, very, very brief introduction to what we tend to be talking about. Stress, again, force going through a tissue expressed as units of force divided by units of cross-sectional area. Strain is the deformation that that tissue is going through when a certain amount of stress is put on it. Stiffness is its resistance, the material's resistance, to that strain. So how resistant is a material to being stretched or compressed or whatever. And then we have the concepts of elasticity and plasticity. Elasticity is how well an object can return to its original dimensions after it's been deformed. Plasticity refers to this permanent deformation that can occur. And when we enter into that plastic region, that's where we get into, when we're past that yield point right here, we start getting into these, this realm where now we have permanent changes to the length of that tissue or to the shape of it. And eventually we get something where we might have a failure point where actually the tension's going back down and the thing just kind of dies off here. It's not a perfect representation, but eventually this material will fail. And if you get used to this concept, you can look at a graph and go, oh wait, okay, that's where the elasticity is no longer intact. That's where we're having a plastic change. This is where the tissue fails completely. And when you can see that, it's kind of cool. So hopefully that helped out. So this was the second video on loads in the body. And I'm thinking for the next one, maybe I will go into torque, start talking a little bit about angular stuff. If I don't do that, instead I may talk a little bit about motion, fundamentals of motion, some more basic Newtonian stuff, and talking about the relationship between linear motions and forces and rotational or angular motions and forces. So obviously drop a comment, you're always welcome to. Give me some feedback, like it, hate it, tell me that I'm just terrible at this, but hopefully it helps some of you. So until next time.